establishing the working schedule of a SAF campaign. We report the main maintenance and repairing steps of a SAF. Okay, these are typical figures. I give ranges. So the operation you do very often is to repair tap holes, metal and slag, and this you have to renew a tap hole every 1 to 3 months. When you repair a tap hole, you let the slag or the metal descend below the tap hole, so you free the tap hole area, and you can extract some bricks and replace them, or you can extract a tap hole cooled box if you have a box, because around the tap hole, I did not go into these details, but around the tap hole you may have a cooling copper cooled box. And this takes 1 day, more or less. The exact duration, the exact period depends on, of course, on the process control. When starting a new furnace, and if people do not respect and do not maintain the temperature, but the temperature fluctuates, of course this will accelerate the wear of the tap hole. Also, if you don't set, if you set the slag more acid, it will corrode more the tap hole, the opening, and this increases the wear as well. And also, you have to take care at tapping operation to not drill, you have to drill in the axis and not to drill like this, or to, of course, then you will destroy the brick. And finally, you have to choose the good brick quality, of course. These are the wear factors which will influence the real duration. But if we assume this, and 1 day, that is the total time that we lose for production in 1 year, you see, 1 to 3 months. 1 month is 12 days. If it's 3 months, it's 4 days per year. You understand?
Yeah.
You understand? No. If I have one tap hole on a new furnace, people are not so experimented. I have to repair it once a month. So per year, I will repair it 12 times. If it takes 1 day, it takes per year 12 days. And for 3 months, it takes 4 days a year. Of course, the main repair of the furnace is the wall reline. Even if you don't reline a new bottom, that is seldom. A bottom is more than 1 year. A bottom is several years. So I do not consider it in. Because when you reline the bottom, it takes not much more time. You do it at the same time when you reline the walls, of course. So SAF reline is typically made every year. But some SAFs work longer time, up to 2 years or even 3 years. The duration of this major repair is 15 days, and it depends on, of course, again, on process control and on refractory quality. Actually the same factors. And per year, if you have one repair per year of 15 days, it takes you 15 days. If you reline it every 3 years, 15 days every 3 years is 5 days per year. Then you will have other key part maintenance repairs, which require stopping of the furnace. These mainly, it can be about charging devices. I told you that the charging pipes where you must change it. This requires, even if you prepare everything, it takes you 1 day. The cooling parts also, of course, changing such a cooling requires to cool the furnace, and okay, more or less it takes you also 1 day. And changing something on the off gas line is also required from time to time. The PC, post combustion chamber, in the cooling, in the spray cooling, etc. Of course, this is very variable. There is no rule, but more or less the period of doing that is you have one such key part to repair or to change per month, one per month, and it takes you something like 1 day, maybe less than 1 day, maybe more than 1 day, depending, but the magnitude is that. So this is 12 days a year. So if we make the total, the addition of the total shutdown time, we have the range is 4 plus 5 plus 12 is 21 days, and the maximum is 12 plus 15 plus 12. This is 39 days. So roughly the range is the furnace will be stopped 20 to 40 days a year, and the real operations time will be, instead of 365 days, it will be 326 to 344 days of operation. Then this means, if I multiply this by 24 hours a day, 7,100 to 8,250 operating hours per year. And if now I assume a real availability of the furnace, availability means more or less when I have the power on, when I'm melting, of 95%, which is for me correct. Could be a bit more, could be a bit less, but it's the magnitude. Then I see that the furnace provides 7,400 to 7,800 productive hours per year. That is typical. That is typical range. And for me, that is very roughly comparable to an year.
Yeah.
Do you have questions about this? It's just a magnitude, of course, can be variable. And if you lose, it strongly depends on the quality of the bricks, on the quality of every key part, of course.
쪽으로 한번 세우면 다시 다 드러내고 해야 되는 그런 케이스니까요. 가장 크리티컬 포인트가 테프리스트. 테프리 안 되면 스톱이죠.
Okay? Okay, we come to the end of this presentation because the next slides are slides of, of basics, oxide constitution, reactions, adding and diagram.
Sorry, previous
Yes.
picture, before picture.
This one? No.
Next
Next one.
Yeah.
Ah,
Please explain.
I explained this. In principle, it is the same like this. But actually, it is a, you see, it is a thermodynamic value. It is a enthalpy, free enthalpy of these oxides, and the free enthalpy is a measure whether an oxide is easy to reduce or difficult to reduce. So you see, at the top, having the smallest, because it's essentially, you see negative values. It's 0 and -200, etc. So the first line is nickel oxide with a small delta G, and this indicates that nickel oxide is easy to reduce. And you see at the other end we have CaO and Al2O3, which are the most difficult to reduce. And in between we have chromium, manganese, silicon. I have it not all to make it more simple. Huh? In the handbooks you find many lines and you cannot read it. And so basically it's the classification of the oxygen affinity of the easy or difficult to reduce of an oxide, but since it's a diagram, it brings more. And what does it bring more? It brings more on two things. On the influence of temperature. You see that in case of CaO and Al2O3, if when increasing the temperature over 2000 degrees, you have an inversion. That is, under normal conditions, 1600 degrees or 15 or 1400 degrees, the highest affinity is CaO, but at higher temperatures, alumina is going to be more affinity with oxygen. And the second interesting point is that you have the curves of CO and the curves of CO at atmospheric pressure, and this is CO at you see 100 pascals, meaning under vacuum conditions. And you can see that deduced from this, you can say that carbon giving CO can reduce all this at 1600 degrees. 1400 degrees, it's about the same height. So carbon can reduce SCO2, MNO, etc. But it will not, carbon will not, under atmospheric pressure, carbon will not reduce these two, alumina and Cl. But you see also that if you work under vacuum, then carbon can reduce alumina. Okay, these actually this is thermodynamic, and that means equilibrium. But of course, you see that in case of at crossing of the two lines, it is equilibrium, and if you want to reduce it with a certain strength, with a certain speed, then you need to have a distance. You need to be behind equilibrium. Okay. That the answer?
No. Okay.
Oh.
You said the distance.
Yes.
In this graph, can you explain about distance?
I say the following. You see, at at 1400 degrees, you see carbon can reduce MNO. Okay. What I wanted to say is that if you adjust on the crossing of the two lines, it will be a slow reaction, not very rapid. And you must have a distance. For instance, chromium has a distance, meaning that you are not just at equilibrium. So it is going more rapidly. Yeah. But in case of MNO, I'm surprised that we are just on this line, because MNO is well reduced by carbon. There is no doubt. MNO, manganese oxide. So you understand? I'm a bit surprised that this, okay, that we are just on the equilibrium for MNO at 1400 degrees. I was expecting that we are beyond equilibrium. Because at the crossing of two lines, of this line, this means that you are just about to begin to have a reaction, but not kinetics or reaction will not be rapid. Okay. And about this was clear. You remember? This is the classification of the elements at about 1600 degrees, 1600 degrees. These are the reactions. These are the very bases of. Okay.
In this graph,
Yes.
You said when the temperatures here, CO and like MgO.
Yeah.
This point is to start reducing.
Yes. Yes.
And if the temperature is higher point,
For instance, if you take at this temperature, 1400 degrees, you can see that alumina cannot be reduced. Or at lower temperatures they are not liquid, but if I take and yes, the conclusion is that you see even chromium cannot be reduced. Where is chromium?
Chromium, yes.
Chromium requires high temperature to be reduced, and in practice it is reduced only in liquid state.
Yeah. So in case, how can I determine if the reducing is appear or cannot?
You can see that for all these, at this, for instance, for FeO,
Yeah.
CO is here.
Here, yes.
That means that the carbon has a higher affinity for oxygen
Yes.
than FeO.
Yeah.
So if you put together carbon and FeO, you will end with Fe and CO. That is the meaning. You understand?
Yes. FeO reduced
Will be reduced by carbon.
by carbon.
But also, you can also say the following: if you have look, if you have only NEO and you have Fe, you will NEO will be reduced by Fe, meaning NEO will be reduced to Ne, and Fe will give FeO.
FeO. Yeah.
You understand?
Yes. So that means Na is reduced.
Yeah.
But this is not.
Yeah.
So did the cross and the
This is with carbon, because carbon is a special element, because carbon is the most popular and the cheapest reductant.
yes.
But of course, if you have FeO, you can reduce FeO using silicon. People do that in steel making. And this is shown also here, because the SeO2 line is below all this. So Se or Al is also are also popular reductants, but they are popular, but they are more expensive than carbon.
Yeah.
So in the SAF, because in steel making you use silicon or aluminium, just it is for for fine tuning at the end to deoxidize steel, very low amount. But here in the SAF, you do large reduction, big amount, and you need you have seen more than 100 kilo carbon, and for this carbon is cheap. You cannot use aluminium for this.
왜 이제 죽도시장 구경 안 시켜줬나?
죽도는 저번에 왔을 때는 못 갔었죠.
어제 또 가자 그랬는 거 아닌가?
어제는 근데 시간이 어중간해가지고 다시 넘어서 갔는데 10시 반에 예약해가지고 또 시내 가야 되고 그래갖고 시내 쪽으로 바로 갔거든요.
종종 저기 저 죽도시장 거기 좀 있으면 나가는데 그러면은 뭐 거기 와서 구경시켜주고 종종 받아오면 내기든지 그렇게 나와버렸는데
일단 오늘 그 이분이 5시 전에 일단 전화를 해야 돼가지고 들어가야 된다 하시니까
해보시네.
Yes. Today we finished